So up to this we have seen in the last class, that is the properties of ionic compounds. Ionic compounds conduct electricity, but no conduction is observed in solid state because in solids the ions are very rigid and they are fixed in the lattice positions. So they are not free to move here and there to conduct the electricity, but they conduct electricity when the substance is molten or dissolved in aqueous solvents. When it is dissolved, then the anions and the cations are free to move. And also in the molten state also, they are free to move. So the ionic compounds conduct electricity in molten state. And secondly, because of the crystal lattice arrangement. You know what is a crystal? In crystals, the ions are arranged in a regular pattern. Because of the regular pattern, the crystal will show very high melting and boiling points because of the strong electrostatic attraction. So the charged particles are fixed alternatively, a positive charge and then a negative charge and then a positive charge, and then it is in a three-dimensional array. Suppose if a positively charged cation is at the center, it will be surrounded by the negatively charged ions in the crystal lattice, and also every negatively charged ion will be surrounded by positively charged ions in a three-dimensional array. And because of this, every ion will experience a very strong electrostatic attraction. And because of this strong electrostatic attraction, the crystals will show very high melting point. And also when you think of the solubility, solubility means there is a concept called the solvation. Solvation, solvolysis, these are all the important chemical terms you must understand. Solvation means one particular ion getting engulfed by the solvent molecules, which is called a solvation. Suppose if a water is used as a solvent, it is called hydration. If ammonia is used as a solvent, ammonation. So this in general, it is called the solvation. Actually, how this solvation is taking place, the solvent molecule, they break the bond between the oppositely charged ions and they will go in between, and then it will solvate every ion. So this solvation process will take place only when the solvent molecule has enough dielectric constant, or only when it has enough polarity. The solvent should be polar. That is why the ionic compounds are soluble only in polar solvents. Water is a very good polar solvent. So water is able to dissolve the ionic compounds, whereas the organic substances, organic solvents, say for example, benzene, toluene, or any other non-polar solvents, they are not able to dissolve, and they are not able to dissolve the ionic substances. So the third property is solubility. The substances can be dissolved by water or in general polar substances. So up to this point we have discussed in the last class. Now we go to the another type of bonding, which is called the covalent bonding. Covalent bonding means sharing of electrons. So in the ionic bond, there is a complete transfer of electron from one atom to the other atom. But in the case of a covalent bond, the electrons are shared between two atoms. Because both the atoms are in need of electrons to get an inert electronic configuration or configuration similar to inert gases. Say for example, hydrogen has one electron, which is in the 1s orbit, 1s1 electronic configuration. And another hydrogen also has one electron, which is also 1s1 electronic configuration. So in order to attain stability, The hydrogen needs one more electron so that it will get the identical electronic configuration with the helium 1s2. So both the hydrogen atoms, so they keep the electrons in common. The electrons are kept common. Now this hydrogen will count the two electrons as its own, and it will show the inert gas electronic configuration. And this hydrogen will also count these two electrons, and it will show the inert gas electronic configuration, or the bond can be mentioned like this H, a bond H. Actually, this straight line contains two electrons. So this is covalent bond formation. So the 1s2 electronic configuration is a helium configuration. Suppose if you take the bond formation of a hydrogen chloride, look at this hydrogen. Hydrogen has one electron, and the chlorine has 7 electrons in the outermost electronic configuration. So the chlorine needs one electron for completion of the octet, and hydrogen needs one electron for the completion of the duplet. So what happens? The two electrons, the hydrogen is donating one electron and the chlorine is donating one electron. These two electrons are kept common. So what happens? This hydrogen is completing its duplet and the chlorine is completing its octet. So chlorine is also getting a stable electronic configuration, and hydrogen is also getting a stable electronic configuration. So the hydrogen chloride molecule is stable, but here it is because of the sharing of the electron. So the bond formed between the hydrogen and the chlorine is a covalent bond. And in the case, so we have seen that there is only one pair of electrons shared, but there is a possibility for sharing of more than one electrons also, electron pairs also. So more than one pair of electron, it is based upon the requirement to complete the octet. So in such cases, you can see a double bond or a triple bond formation. You look at the oxygen. Oxygen is having 2, 4, 6 electrons in the outermost orbit. And another oxygen is also having 6 electrons in the outermost orbit. Now what happens? Both the atoms are in need of 2 more electrons to complete the octet. So what happens? The oxygen, it keeps, this oxygen donates 2 electrons, and that oxygen also donates 2 electrons, and these 4 electrons are kept in common for both the electrons are, both the 4 electrons are kept in common for the oxygen and the oxygen. So what happens? A double bond is formed between oxygen and oxygen. So when more than 2 electrons are needed for the bond formation, 2 electrons, more than one pair, it is also possible. It depends upon the requirement. So what happens in the case of a nitrogen bond formation? You can see here, nitrogen has 5 electrons in the outermost orbit. And this nitrogen also has 5 electrons in the outermost orbit. So each nitrogen needs 3 more electrons to get the completed octet. So what happens? It keeps the 3 electrons in common. So one nitrogen donates 3 electrons, another nitrogen also donates 3 electrons. Now if you count the electron for this nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. So the octet is complete. If you count the electrons of this nitrogen, 1, 2, 3, 4, 5, 6, 7, 8, the octet is complete. So this is how the nitrogen molecule is stable with 3 bonds. See, each bond is having 2 electrons. So 3 bonds are in between the 2 nitrogen atoms. So according to Lewis' concept, the number of electrons which an atom contributes for sharing in a covalent bond is called covalency. So previously we have seen what is electrovalency. Electrovalency means the number of electrons that are donated or gained by an atom to attain stability is electrovalency. According to Lewis' concept, the number of electrons which an atom contributes for sharing in a covalent bond is called covalency. So, according to our previous understanding, we can say the hydrogen has the covalency 1, oxygen has the covalency 2, and chlorine has the covalency 1, nitrogen has the covalency 3. Now look here, as we have discussed earlier, when the atoms are approaching each other, there should be minimization of energy. See, a molecule supposed to be with a less potential energy comparing its atoms. So the atomic energy is higher and the molecular energy is lower. That is why the molecule is more stable than the atom itself. So what happens when the attraction predominates? There is a decrease in energy. When repulsion predominates, there is increase in energy. So when two atoms are approaching each other, actually what is happening is, so let me say this is hydrogen A, this is hydrogen B nuclei. See, what is mentioned in the black color is the repulsive force, and what is mentioned in the green color is the attractive force. So electron is mentioned in the pink color. Look here, the hydrogen A has an attraction over the electron A. So there is an attraction. Similarly, the hydrogen B has an attraction towards the electron of its own. It is EB. But at the same time, this hydrogen will extend its attraction to the other electron also. Similarly, this hydrogen nucleus can extend its attraction towards the other electron also. So these are all the attractive forces existing when two atoms are together. At the same time, repulsive forces also exist. The repulsion between the nuclei, the like charged nuclei, and also the repulsion between electron clouds. So what happens? What happens? Sometimes when the atoms are far away, attraction predominates. When the atoms are closer, repulsion predominates. So in a particular distance, that is the magnitude of the attractive force is more than that of the repulsive force at a particular distance. And that distance is actually the bond forming distance. That is where the potential energy is minimum. So look here, when the atoms are separated for a very long distance, when the atoms are separated, the attraction prevails. When the atoms are forced to be very closer, the repulsion prevails. But there is a particular distance where the attraction and the repulsion balance each other, and the net force becomes attraction, where the potential energy is a minimum. That minimum distance is called the bond length, or the distance at which the atoms try to be together, where the attraction prevails. Say, for example, in the case of potential energy diagram for hydrogen molecule, when the hydrogen atoms are separated for a long distance, see in the x-axis, when you go away from the zero, the distance between the atoms increases. When it goes away, almost the potential energy is zero here. But when the atoms are brought closer and closer and closer, the energy goes below zero and it goes to a minimum. And then further compulsion of the atoms to be together, it increases the energy, and there is a sharp increase observed, and the energy goes on increasing. So this is the distance at which minimum energy is observed, and this distance is called bond length. So this bond length is 0.74 angstrom unit for hydrogen. Actually, this energy, this negative energy is called bond dissociation energy. Actually, this is the energy which is actually released for the bond formation. If you are able to supply the same amount of energy, the same bond can be dissociated. That is why this energy is called bond dissociation energy. So in the entire picture, you have understood the complete theory behind the covalent bond formation. So it is a mere the attraction. The sharing of the electron is another concept, but the attraction and the repulsion and their balances. The whole world is existing because of the attraction and the repulsion and their equilibrium. Everything in the world is controlled by only one factor, which is the attraction. Actually, philosophically speaking, there is no repulsion at all. Repulsion is nothing but attraction towards the negative force. It is the attraction towards negative force is the repulsion. Suppose if you want to understand this particular philosophy, you try to read a book by Napoleon Hill. The title of the book is uh, The Master Key to Riches. It's a very good book. Even you can purchase of your own. You get the book and try to read the book. He speaks about the master key to the riches. That is a key. When the key is operated, you can open up any riches in the world. What he says is that our mind is uh, like a radio station, which will attract the waves. The wave that you are generating in your mind will attract the corresponding wave from the universe. So the whole world is controlled by mere the attraction. So that is what is discussed here. The whole world is existing by the attraction and the repulsion. Actually, there is no repulsion at all. It is a negative of attraction. So this is how the hydrogen molecule is formed. Now look here, hydrogen atom, when they are far away, the energy is fixed to zero arbitrarily. So when they approach each other, the potential energy decreases. And after the minimum value, there is a sharp rise in the potential energy. And this rise in the potential energy is due to electronic cloud repulsion or the nuclear repulsion. So the formation of a covalent bond between two hydrogen atoms takes place at the point which corresponds to the minimum in the potential energy curve. So that minimum energy, it is corresponding to a distance, and that distance is closer than which repulsion predominates, and that distance is called the bond length. And that distance is called the bond length. For hydrogen molecule, the bond length is a 0.74 angstrom unit. And also the energy that is minimized is a 458 kilojoule per mole. So the energy is the minimization in the potential energy, and this energy is also called the bond dissociation energy, because this much of energy is given out when the hydrogen molecule, when hydrogen atoms are brought closer to form the covalent bond. At the same time, if you are able to supply the same amount of energy, the hydrogen bond, the bond between hydrogen atoms will break, and the hydrogens will be generated as hydrogen atoms. So now you can see another thing. This is a different concept for uh, the same covalent bond, which is the overlap of orbitals. What happens to the orbitals when they overlap? An orbital is a three-dimensional boundary in which the probability of finding the electron is maximum. So you should understand the difference between an orbit and an orbital. Orbit is a two-dimensional path in which is traveled by the electrons. Orbital is a three-dimensional boundary in which the probability of finding the electron is maximum. An orbital can accommodate maximum number of two electrons. More than two electrons cannot be accommodated in an orbital. It is according to the Pauli's exclusion principle, which states that no two electrons residing in the same orbital can have all the four quantum numbers the same. So an orbital can have only two electrons. So in an atomic system, the orbital which has two electrons is not at all available for chemical combination. It cannot combine. with the orbital of the other atom to make a covalent bond. So formation of covalent bond between two atoms results by the coupling of electrons with opposite spins belonging to orbitals of outer shells of two atoms. So what is the condition? There should be overlapping orbitals and each should have one electron which are opposite in spin. Look at this diagram. This is the hydrogen molecule. Each hydrogen atom has one electron. It has oneness orbital, and this oneness orbital has one electron, and this oneness orbital has one electron, and these two electrons are supposed to be opposite in spin. So what happens due to the overlap of the orbitals, they are getting an overlapped orbital which is completely filled, which has two electrons which are having opposite spins. So such a direct overlap, this overlap is also called face-to-face overlap or a direct overlap. And this direct overlap results in the sigma bond formation. This is a sigma bond. Similarly, you can think of the fluorine molecule formation. Look at the fluorine molecule. The fluorine molecule outermost electronic configuration is 2s2, 2p5. And another fluorine molecule with 2s2, 2p5. Actually, this diagram, I don't know whether you will be able to understand. I have drawn in a simple manner. You can try at home. See, this is x-axis, and this is y-axis, and this is z-axis. Similarly, for this fluorine, this is x-axis, and this is y-axis, and this is z-axis. And look here, the p orbital has three lobes. P orbital is a triply degenerate. Degenerate means orbitals with equal energy. Triply degenerate. Three lobes, or I can say the magnetic quantum number of a p orbital is -1, 0, +1, which means which has the three orientations in space. One orientation is along x-axis, another orientation is along y-axis, and another orientation is along z-axis. And among the three orbitals, two orbitals are completely filled. See, each orbital can have two electrons. So two orbitals are completely filled. One orbital is having one electron. So among the three orbitals, two orbitals are not available for bond formation, and these two orbitals are shaded. See, the px and py orbitals are shaded because they are with the completed electronic configuration. They have accommodated to their full capacity. So two electrons are present in x orbital, px orbital, and two electrons are present in py orbital. So they are complete. So what is remaining is only the z orbital, pz orbital with one electron, and another pz orbital with one electron. So these two orbitals overlap, and this overlap is also a direct overlap because z is considered the molecular axis. So the orbitals along the molecular axis will have a direct overlap. So this also forms a sigma bond. So in the case of hydrogen, it is s orbital overlap, which results in the sigma bond. In the case of f orbital, it is pz overlap, which results in the sigma bond. Now you can see the overlap between hydrogen and fluorine. So hydrogen is having oneness orbital. As we have discussed in the previous case, the fluorine is having px and py orbitals, which are complete and which are with two electrons each, and which are not available for the bond formation, and only the z orbital is available. So s orbital and z orbital, pz orbital, they can have a direct overlap, and that will also result in sigma bond. So you should understand S or PZ or S and PZ when Z is considered the molecular axis. Suppose if X is considered the molecular axis, then Px and S will form sigma bond. Now, when you discuss this oxygen molecule, you will understand what I really mean. When you think of the oxygen molecule Oxygen outermost electronic configuration is 2s2 2p4. And this oxygen is also 2s2 2p4. So one orbital is completely filled, which is not available for bond formation. And the other two p orbitals are having one electron each, which can involve in overlap. And if you take the z-axis as the molecular axis, you think of one lobe along the x-axis, another lobe along the y-axis, and another lobe along the z-axis. And similarly for the other oxygen also, one lobe along the x-axis and one lobe along the y-axis and another lobe along the z-axis. And these px orbital is completely filled. So y and y can overlap, and the pz and pz can overlap. You can think of here the pz and the pz has a direct overlap, where the overlap is strong and also overlap is face to face, whereas the py and the py have a side to side overlap or a lateral overlap. And because of the lateral overlap, a weak overlap is resulted. And the direct overlap is a sigma bond, and the lateral overlap is called the pi bond, which is weak. That is why for oxygen, two bonds are between oxygen and oxygen. One is a sigma and the other one is pi. And in the case of nitrogen molecule, you can see it is S2P3. So all the three orbitals of the P have one electrons each. So what happens? There is a possibility for the overlap of all the orbitals. So in order to make a distinction, I have drawn the orbitals in various colors. See, the px orbital is drawn in brown color, and the py orbital is drawn in pink color, and the pz orbital is drawn in green color. You can see that the green colored z orbital has a direct overlap, forming sigma bond, whereas the brown colored they have a lateral overlap, and the pink colors they have a lateral overlap. So this is how the nitrogen and nitrogen, there are three bonds between them, whereas one is a sigma bond and the other two are pi bonds. So these are all the things we supposed to discuss in the covalent bonding. I suppose you might have understood everything. Anybody has any doubt?